So what we're going to do in this video is talk about how we can calculate pHs of strong and weak base solutions. So we're going to start with solutions that their formulas are already bases, and we ultimately want to find out what the pH is of these. So we already have talked about strong bases a little bit, but one of the things that you have to still be able to do is we still need to be able to identify what a strong base is from a weak base. And as you recall, okay, our strong bases, okay, are all of our group 1 elements with hydroxide and group 2 elements from calcium on down. Okay, so remember that, all group 1, and then group 2 from calcium down with hydroxide ions. Okay, so the difference in our equation from acids is strong bases will just dissociate into the ions that are present. So again, how would I write the dissociation of lithium hydroxide? And you should be writing that as lithium hydroxide will break down into Li plus ions plus OH minus ions. Okay? No water is added. Unlike acids where we add water, you need to make sure you do not add water here. So if I have strontium hydroxide, what would that break down into? And you should have written Sr2 plus 2 OH minus, because we need to remember our ionic equations essentially. There are 2 hydroxides there. Okay? I've already done that, so I don't need that. Okay, but then what about what happens when you have NH3? Okay, now when you have weak, okay, bases, without hydroxide in them, okay, whenever you have weak bases without hydroxide, then you add water. Okay? So, very important distinction right here of with weak bases without hydroxides, now you will have to add water to them. So, NH3, if I have NH3, I actually now have to add the water to this, remembering that weak are going to be in equilibrium, and what happens is the water becomes the hydrogen ion donor, so I get NH4 plus OH minus. And now you have a hydroxide. And this is the only way to get the base part of the equation. We have hydroxides up there. Okay, you must add water in order for us to get the hydroxide for a weak base. Okay, so this is still our base molecule indicator no matter what we have. Okay, so when we're calculating pH, you do need to recognize, okay, do I have a strong base or a weak base? So if I want to calculate the pH of a 0.25 molar solution of KOH, when I read KOH, my mind has to go, ooh, strong. Okay? And once it's strong, then KOH forms K plus ions plus OH minus ions. And we are strong, so the equilibrium shift is 100% to the right. Which means then, if I have 0.25 molar KOH, I also have 0.25 molar hydroxide. Okay? Now, one of the things to remember is all of our problems are always going to ask us to calculate pH. Up until last week, you probably never even heard of POH. However, we want to use POH to calculate this. Okay? Because that would be so much easier than converting it to H3O plus right away. So I just want to use POH, and I want to find out what that POH is. And so the POH of this comes out to be 0.602. Okay? But the problem did ask for pH, and they're always going to ask you for pH. So you just need to remember that pH plus POH equals 14. So the pH equals 14 minus POH. So the pH of this solution is 14 minus 0.602, which means I am still a very strong base at 13.4. Okay? So, just a few review things. I know we've done this, but now we got to talk about weak bases. And right now, the only real weak base you've worked with is ammonia. But there are other weak bases. Okay? So, this compound right here, okay, is actually a weak base. And you're not going to be used to these right away, so you're just going to have to be told that, hey, this is a weak base, and that's going to tell you how to write the equation. So this compound right here, you're being told that's a weak base. So then what would the equation be for this? Well, hydrogen still becomes the hydrogen ion donor, and this is what becomes really weird. So you are going to just tack that hydrogen on to that hydrogen right there. So this becomes CH3 N2H3, which is now a plus. And then that water becomes an OH minus. So in our Lewis acid-base pairs, this is the acid, this is the base, and then conjugate-wise, this is the conjugate base, and this now becomes the conjugate acid, which, if you remember from last week, anything that had that plus charge was an acid. Okay? So, new ways to think about things. One more equation here. So here's another one. Okay? And again, you are being told, and until you get used to doing this a lot, you kind of have to be told that, hey, this is a base. Okay? So knowing that, water becomes the acid and is the hydrogen ion donor. Okay? So that means then that this has become CH5NH plus OH minus. Okay? And again, notice in both of these, and I don't think I pointed it out up here, here is your base. Here is your base. You have to get that OH to get that base. Then notice how I tacked this hydrogen ion just onto the end of that. Okay? Never ever put that hydrogen and make this C5H6N plus. I don't ever want to see that, so don't do that. Okay? Particularly if you want to know why, draw the structure of that. Okay? And you'll see why very quickly. Okay? So, new things to get used to, new types of bases. But now we have weak bases. What we want to do is calculate what the pH of weak bases are. And honestly, this is exactly the same as calculating the pH of a weak acid. The only thing that you're going to have to deal with is a couple of things to remember. Number one, we're going to have a KB instead of a Ka. Okay? But this all still starts with writing the formula. So I have NH3 plus H2O. That's going to give me NH4 plus OH minus. And again, I can't stress enough, that right there tells you that you have a base, okay? And we're just going to make our ice chart, okay? So, making our ice chart, we have 15 molar solution, which is pretty strong, by the way. Water, we never care about, okay, because it's not part of the equilibrium constant expression. This is 0, this is 0, minus x, x, x. So 15 minus x, x, and x. Okay? So if I write my equilibrium constant expression, it is now Kb equals the concentration of NH4 plus times the concentration of OH minus all over the concentration of NH3. Okay? So there's my equilibrium constant expression. And my Kb for this was 1.8 times 10 to the minus fifth. So now I'm just going to go 1.8 times 10 to the minus fifth equals x times x all over 15 minus x. Okay? Now, same math as before, 10 to the minus 5, so I can just cross out that x. So this equation is going to be 1.8 times 10 to the minus fifth equals x squared times over 15. Okay? Solve for the x squared. Okay? So multiply both sides by 15. That cancels that. And then take the square root. So doing that, you should get a value of x that is equal to 0.016. Here's the issue. Okay? By the way, this is molar now. You need to remember what x is. And x is the OH minus concentration. Okay? So, the concentration of OH minus is 0.016 molar. Which means the question asked, what is the pH? But you have to remember what you're going to find right away is pOH. Okay? This is one of the things that people sometimes forget that that's what they're doing. This is why I need you to write stuff out right away. Don't take our little shortcuts that we like to take. So then pOH is minus the log of 0.016. So pOH equals, I don't know. pOH is 1.79. So the pH is 14 minus 1.79. So pH is 12.20. Okay? So with weak bases, a lot of the math is the exact same math that you will normally do. You just have to be used to different types of equations. So I want you to see one more. So, oh, by the way, sorry. We can still determine percent dissociation. Okay, and remember percent dissociation, okay, would be the concentration of OH minus ions all over the concentration of NH3 ions times 100. And remember, this is original. So in this particular problem, it would be 0.016 divided by 15 times 100. Oops. Which in this case is 0.106%. So, not very much dissociated. We are actually shifted very far to the left. Okay, now one more. So, what if we don't have something like ammonia, which we're kind of getting used to? What if I have methylamine? Okay, and I want to change this. I want to change this to a 2.5 molar solution of methylamine. Okay, and I do have to tell you what these formulas are. Okay, and you do then need to see, you look at this and say, well, that's not an acid, that's got to be a base. So those are some of the things that we're just going to have to get used to. So I have CH3 and H2 plus H2O, and that's going to give me CH3 and H3 plus OH minus. And we're just going to make our ice chart. Okay, and I have a 2.5 molar solution. Water never matters. 0, 0, minus X, X, and X. So 2.5 minus X, X, and X. So this is a KB, and again, KB because of that. Okay, so you gotta look for that OH in your equation. And so the KB is the concentration of CH3 and H3 plus times the concentration of OH minus all over the concentration of CH3 and H2. That's my KB expression. So then filling in 4.38 times 10 to the minus 4th equals X times X all over 2.5 minus X. Okay, 10 to the minus 4th, I can get rid of X. That can go away. So then 2.5 times 4.38 times 10 to the minus 4th equals X squared. And then I'm just going to want to square root both sides. And so X comes out to be 0.001095. And now remember that that X is our OH minus concentration. And so I'm going to calculate POH. And POH in this problem comes out to be 2.96. So pH is 14 minus 2.96. So pH is 11.04. Good? So that should be enough for you to solve problems with POH and weak bases. You should now do worksheet 4.